Let's continue the topic of probability in sampling by talking about random variables. A random variable is a variable whose values are determined by a random event. So think about when we randomly select it from the college roster. We said that the random selection of a unit was a random event. So a random variable is any variable whose values are determined by that event. Well, what variables did we have when we selected a student? We have the student's name, we have the student's ID number, we have the student's class standing. If we were doing this from an actual college roster, we'd have many more variables such as their major, their gender, and so forth. All of those would be random variables if the selection of that student was at random. So an example of a random variable is the class standing of students that we randomly select from somewhere college. Now there are two primary types of random variables. Discrete random variables assume values that are from a specific and finite list, such as the class standing of students. They can only be one of four discrete values: freshman, sophomore, junior, or senior. Contrast that with a continuous random variable that can assume any value in a specified range. For example, what about height? Height can be anything within a specified range. And in fact, I'm going to use this as an example to show you a continuous random variable. And we're going to also select units from a continuous random variable, just like we did in an earlier presentation or an earlier video from a discrete random variable. So I'm going to call up R. And if you want to follow along, I am going to be using the sampling probability continuous file. Now the data that we're going to work on here is based upon U.S. Census Bureau data that puts the height of females ages 20 to 29 as following a normal distribution. You remember that's a distribution that looks like a bell-shaped curve. We have discussed that in the past. With a mean of 64.1 inches and a standard deviation of 2.75 inches. Now notice this random variable, and I'm going to call it a random variable because we're going to select at random from this population. This random variable can be anything because it's a height. Now we have some discreteness to it because we don't measure out infinitely precise. But theoretically, we could have 64.079328 as one of our values. In fact, we can have any value as height. So that's why we refer to this as continuous. Let's take a look. I'm going to go ahead and run in order to get what we've seen before, and that is a normal curve. Here's an illustration that is now illustrating the population of American females ages 20 to 29, and it's focusing on their height. So this is what the distribution of height looks like when dealing with females ages 20 to 29 from the United States. Here's their heights. Now we can take a sample of size 50 from this distribution, and there's some nice functions in R that lets us take random samples from a distribution in which we specify it being normal with a mean of 64.1 and a standard deviation of 2.75. So I'm going to take a sample of size 50. just like I took a sample of size 50 from Somewhere College, but this time I'm taking it from a continuous distribution where any value is possible, even though it's theoretically possible, the chances of us getting some value higher than 75 or lower than 55 are really slim. Most of the values, as we see from this curve, should come from near around 64, with fewer and fewer as we get farther and farther away from that. So let's go ahead and take a sample, and because I'm dealing with a quantitative variable, I'm going to look at a histogram rather than a bar chart, and here's our histogram. Now this histogram helps show us the heights of the women in our sample. Notice that even though it is peaked a little bit in the middle, it's not a normal curve. When we take 50 random events, that doesn't exactly mimic our population. So our population looked like this, but our sample looks like this. And in fact, if I take another sample, the histogram looks different. And I could keep doing that. I could keep going back and repeating these lines and taking new samples, and each time I cannot predict what the histogram will look like. But what we found out when we were looking at the Somewhere College students in the bar graphs is that if you take lots and lots and lots and lots and lots and lots of samples and combine them together, you can predict what should our samples look like when we combine many samples from the same population. They should look like this. They should look like the original population. So now let's try this. The only thing different from what we did before is that now we're sampling from a continuous distribution instead of a discrete distribution. So I'm going to take 1,000 samples. Remember that I did that before with Somewhere College? Well, I'm doing it here. Each one is going to be size 50. I'm taking 1,000 samples of size 50, and now I'm going to plot all those samples combined. Look at that. Isn't that spectacular? When we take multiple samples using random sampling, a random event in which we have no idea what number we're going to get each time, it's totally random. If we do this enough times, we can predict that the outcome is we'll end up with a distribution that looks like our population distribution. In fact, let me go ahead and stick the normal model right over top of this so we can see. How about that? I have put a normal curve right over the top of the histogram so that you could see how repeated sampling leads us to the population. So even though we take a single sample and we cannot predict what it will look like, we know that if researchers were to continue to take samples, that in the long run, they will mimic their population. So we've looked at a discrete random variable, class standing of students at Somewhere College, and a continuous random variable, heights of United States women ages 20 to 29. And in both cases, we saw that the rules of probability work in that repeated sampling, though unpredictable, is predictable in the long run.